Okay, thank you, Nikki, for having me here this evening. And to start, what I'd like to do is to first of all thank Geobus. It's hosted here at the University of St Andrews, and really the Scottish Geology Trust for inviting me to come talk to and speak to all of you this evening. And in many ways, what I'd like to do is I don't want to necessarily focus purely on the rocks in terms of the title of my talk, 3 billion years of Earth history as recognized here in Scottish geology, but to highlight what the Scottish Geology Trust really likes for us to think about focusing on, and that is this richness of the geological heritage that we have here in this relatively small country with its enormous geological diversity. And so I want to really think about some of the ideas that were created from studying the Scottish rocks, as well as the fact that we have these rocks here that are free for all to come and see and enjoy. We're all aware of the North Coast 500, as it's called, Scotland's version of Route 66, that has been, depending on how you want to look at it, a boon to the economy of Northern Scotland, or really a bit of a nightmare given the amount of increase of road traffic. But nevertheless, it highlights the fact that we have this heritage, both culturally, that people enjoy, and if we change the NC 500 to what we can think of as the NC 3 billion, we could link that then into the geological history and heritage that we have. And really what I want to do is take the time to look at the ideas that have led to the foundation of what we call the science of geology today. Those originated here in Scotland, as most of you know. And I'm going to touch upon some of these ideas that many of you will already know about and have already heard about, but hopefully I'll be able to present a slightly new version of those, or a slightly more insightful version of those, and perhaps something that you didn't know about those that is quite interesting. And we want to talk about the concept of deep time, that is geological time. Think about the evidence that people generated from understanding the origin of granites and what that gives us in terms of understanding continental crust, that is the platform of rocks that we live on and the societies are built upon today. Faults here in Scotland that have contributed to one of the grandest concepts that is part of earth science, geology, and that is plate tectonics. And then even look at some of the rocks that are preserved along the west coast of Scotland that allow us to understand the creation of ocean basins. This is a geological map of Scotland, a highly simplified one that many of you have seen and looked at and have probably used in your own journeys around the geology of Scotland. And in many respects, what I like to use when I show these maps, or the term I like to use when I show these maps, is that what you're looking at here is a timescape. We're all familiar with the concept of a landscape, where you look at a map and you see mountains, valleys, rivers, hills, etc. When you put the geology onto that type of a map, what you see then is that the rocks exposed at that particular locality on Earth's surface were formed at a particular time in Earth's past. Therefore, standing there at that position, that landscape, is actually taking you back in time when those rocks were first generated. Therefore, you have this concept of a timescape, that we know what was being formed at that position on Earth's surface at that time in the past. And so for us to take our geological journey around Scotland, this 3 billion years, we're going to do it in a somewhat counterclockwise fashion. The red dots are the localities that we're going to visit, at least through our medium of Zoom, and highlight some of the features that have led to these fundamental ideas that have shaped our science and our understanding of the planet that we live on. And what I want to finish with, hopefully if I have enough time, are 3 geological vignettes, if you will, and that is studies that are ongoing today that allow us to understand aspects as varied as the formation of the moon, climate change. We're all aware of that today, and what we want to do to try and understand climate change as it's occurring now is to see how climate change occurred in Earth's past, and in some instances in Earth's very deep past, with some of the most severe climatic episodes that the planet ever experienced. These are known as Snowball Earth. And touch upon biospheric evolution, and that is how life evolved from simple forms to what we see today. I'm going to start by talking about revolutions. And when we are taught science from elementary school right on up through university, three major revolutions are always highlighted. The Copernican Galilean, in which the concept of Earth as being at the center of the universe was replaced with the fact that it's not at the center of the universe, that the sun and planets orbit the sun. The Newtonian revolution, which gave us the views, the mechanistic views and the mathematics to begin to understand our universe in a way that was quantitative and could be described by mechanistic terms. And then the Darwinian revolution, which essentially made man, humankind, an integral component of nature, that we weren't distinct from, but were a part of nature. But as fundamental as those three were, one that was as fundamental in terms of shaping our thinking about our relationship with the planet that we live on and the planet's position in our solar system, and for that matter in the universe, can stem back to this rather austere looking gentleman up in the right hand corner, James Hutton, which we all know, often termed the father of geology. And his revolution is one we can think of as deep time. That is, he gave us geological time. Put yourself back into Hutton's era, and what Hutton was faced with when he thought about Earth processes, geological processes, natural processes shaping the planet, was that the amount of time available for these processes to operate was rather limited. In many cases, the concept of the Earth only being 6,000 years old was accepted by an array of people, including Isaac Newton, the Venerable Bede. That was supplanted somewhat by William Thomson, Lord Kelvin, less than 100 years ago, or a little over 100 years ago, actually, who was considered in his day to be the second greatest physicist ever after Newton, in which he undertook an analysis looking at the creation of the mass of the sun due to the burning of hydrogen to form helium, that at the age of the sun, given that the Earth probably formed at the same time the sun did, would have been around 20 million years ago to maybe 400 million years ago. And Lord Kelvin actually felt that 20 million years was closer to the reality. And yet Hutton was talking about time that we now know we can see the Earth is in our solar system as being around 4,567,000,000 years old. Now, how did Hutton come up with this at a time when we were talking about thousands of years, let alone millions, tens of millions of years? He did it from a very humble, simple thought process. And this shows us his genius in that it's often called the paradox of the soil. And the reasoning Hutton used was this: soil has been around since the time of history, mankind's creation of history, and therefore soil was probably always around. And yet, you could go out during a storm and see soil continually being washed off a land surface. Hutton, being a farmer, he did this, and he actually calculated the amount of time it would take under storms to remove all the soil on Earth's surface. And it wasn't that much time. And so Hutton did an enormous mental leap. He thought, well, since soil had to always be around, and yet we always see it being washed off the land, it therefore must have always been created in some manner. And this led him to perhaps one of the most poetic statements in geology: the result, therefore, of our present inquiry, that is thinking about soil formation, is that we find no vestige of a beginning, no prospect of an end. And he termed this idea of the creation of soil and its washing off the land his cycle of decay and cycle of rejuvenation. The cycle of decay was erosion. The cycle of rejuvenation was the creation of land surface through processes such as volcanism. Hutton realized that because we have volcanism, this must mean that Earth's interior was hot, and therefore heat, we know, flows from hot to cold, and Earth's surface would have been colder than Earth's interior, and therefore heat would have flowed upward. And we see this then in terms of the eruption of volcanism and lava flows from magma at Earth's interior. This cycle of decay and cycle of rejuvenation, if you're sitting in an earth science or a geology class today, we have another term for it, and that's called Earth system science. This idea that the processes that operate across Earth's surface are linked, intimately linked. And this was a concept that was fundamental to Hutton's thinking 250 years ago. His proof for this came from our first geological stop on our tour around the 3 billion years of Scotland. Probably many of you have been here. This is Sicker Point. It's just about 2 hours south of where I'm sitting talking to you from. The map in the top left-hand corner shows a red dot. And those red dots, when I show you the maps of other localities, is where we're going to be located geographically in terms of Scotland. And here at Sicker Point is this remarkable relationship where we see underlying rocks standing subvertical, standing on end. They're standing upward like a deck of cards. There's a surface that I've highlighted in black that separates those from layers of rock that are sitting at a much less tilted angle. If we go back to use Hutton's reasoning, what he recognized is that those subvertical rocks would have had to have been essentially deposited as sediment layers on the seafloor subhorizontally, that they then had to be lithified, turned into rock, tilted upwards to give them their vertical position. Those rocks would have had to have been uplifted off the seafloor to become eroded. This dark line that I'm showing you, those tilted sediments then, or those sediments that are tilted now, would have had to have been deposited horizontally onto that surface. All of those layers then had to have been lithified and tilted themselves, and then you had to have present-day erosion to form the outcrop that we see today that we call Sicker Point. Now, Hutton had no idea how long that took, but he knew it had to be a considerable amount of time, and that this process must have been going on ad infinitum. Here we see it preserved in the rocks, the formation of a land surface, its erosion, the formation of another land surface, its erosion, the formation of the present-day land surface, its erosion. And this led him then to the recognition of this concept of deep time, geological time. If we now place what we understand and recognize the ages of these rocks onto Hutton's reasoning, we can see that that surface that separates these subvertical layers from the layers that are sitting there in a slightly, are just slightly tilted, these Devonian rocks overlying these Silurian rocks, that surface separating them represents 60 million years of time, and the underlying rocks are themselves around 440 million years old, and the tilted rock layers, these Devonian rocks, are about 380 million years old. This was Hutton's recognition of the concept of deep time. Now, you can tell from my accent, I'm not a native, and if somebody would have asked me 25 years ago before I came here, what's the one rock that would represent Scotland to a non-geologist, it would probably be granite. Scotland is known around the world in terms of granite. This is what people think about, and I know because I've talked to many people who are non-Scots about Scottish geology. And the thing about granites is, and our understanding of granites is that we know now that we live on continental crust, and continental crust is one of the two major components of crust that forms our surface, the other being oceanic crust. But continental crust is comprised of a number of things, but largely is comprised of compositions of igneous rocks that can be classified as granitic. So the understanding of granites and how they form will allow us to understand in large part how continents form. And if we transplant ourselves back 200, 250 years at the time of Hutton, the origin of granite was something that was really debated quite strongly. And on one hand, you had the greatest mineralogist of his day, Abraham Gottlob Werner, who made the claim that granites essentially precipitated out of the ancient oceans. In Hutton, whose pedigree was nothing at all like Werner's. Werner's still considered one of the greatest mineralogists of all time. Hutton was a farmer. He was educated. He had done some work as becoming a doctor. But he disagreed. He said, no, he said, this can't be the case, that we're looking at the formation of granites due to their relationship to igneous rocks and volcanism. And Hutton needed to prove that. And our second stop then in our great ideas, geological heritage and their ideas, will take us up into the central Grampian Highlands at a location of Glen Tilt and Blair Athol Estate. And of course, the person sitting there that you see is not Hutton, that is Ian Stewart in his documentary Men of Rock, which is now probably about 18 years ago. And what I've highlighted there in red is the granitic rocks that you can see cutting through and intruding the bedrock that Ian Stewart is sitting on. And this is Hutton's sketch. And he shows exactly that same relationship where these granites are intruding, migrating through pre-existing rocks. And in one simple observation, Hutton disproved the greatest mineralogist of his time, and like I said, one of the greatest mineralogists of all time, to recognize that granite and continental crust had to be formed by molten rock. Now, the idea of granite and what it means and how it's related to continental crust is something that is in part debated to this very day. Here is a diagram that I've taken out of a publication. It is a synthesis of our understanding of the generation of continental crust. It was published, this paper was published just a few months ago. And what you see here is a graph. On the x-axis is time going from left, about 4.5 billion years ago, time of Earth's formation, to the right, 0, the present day. The y-axis is giving us percentage of the amount of continental crust that existed at a particular time in the past. Those colored curves represent guesstimates, estimates, predictions, if you will, hindcasts of various people who have tried to examine the composition of continental crust, various geochemical characteristics of it, to guesstimate how much continental crust existed in the past. And what you can see there is this enormous range in guesstimates as to how much continental crust existed in the past. That is, how much granites existed in the past, in a sense. The graph on the right is something completely different. Now, I apologize to this because here the x-axis is giving us time, but in this instance, you're going from the present day on the left to more or less the formation of Earth 4.5 billion years ago on the right. And the y-axis is the amount or number of the mineral of crystals of zircon. Zircon is a mineral that contains uranium. It's important in terms of our ability to radiometrically date rocks. And it is a significant, well, it is not necessarily a significant component, but it is a component that you can find. You can find it in granites. It's quite common in granites. And what this particular graph is showing us is that there seems to be these pulses, and some people have actually called this graph the pulse or the heartbeat of the planet. And it tends to infer that the amount of continental crust that was generated through time occurred in pulses. Now, there's a great debate about this, whether this represents an actual record or if we're looking at partial preservation of records. But the point is that I want to make is that even to this day, this idea of how we relate a feature of granites, such as this graph on the right, which is showing us the amount of zircons, which can be used as a proxy for, in part, the amount of granites, because zircons are common in granites, to the graph on the left, which shows, in most instances, this progressive, steady, and in some instances, exponential increase in continental crust. How you can relate these ideas of pulsations to a steady state or exponential increase in continental crust is something that people are discussing today. All of it as a consequence of Hutton's ideas about how we can understand the formation of granite. This is what the foundation of these modern day studies are based on. Now, what's interesting, of course, is that when you look at these diagrams of continental crust, and now we're going to go right up into the northern parts of Scotland, is that we can come to Scotland to begin to try and test ideas about these formation of continental crust, and particularly ancient continental crust, because this outcrop, which is perhaps the second most famous outcrop in all of Scotland after Sicker Point, is a road cut on the road that takes you up to Durness. And what you can see here are what are thought to be mid to lower continental crustal rocks that are 2 to 3 billion years old. So here we have exposed continental crust that records its formation 2 to 3 billion years ago, and people come from all over the world to study these rocks to try and help us understand the evolution of continental crust through time. But what I want to highlight that's as significant is the idea of how the crust form is the fact that what you see here is that we're saying it's mid-lower continental crust, i.e. this is crust that has formed 30 to 40 kilometers down, 2.5 billion years, 3 billion years ago, and it's now sitting at 100 or 200 meters above sea level. And we got to begin to question, what were the processes, or try and understand the processes by which we can infer that these rocks formed tens of kilometers below our feet, and then how these rocks were actually exhumed and uplifted and to be exposed on Earth's surface. And we can go to our second geological hero then, who did give us the insights as how we can understand where rocks were formed at depth. And this is George Barrow, who is working in the Angus Glens. And this is a photograph of Glen Clova that was taken just a couple of weeks ago. My wife and I, on our anniversary, went up and had a lovely walk there. And here's a beautiful landscape. But of course, George Barrow was looking at these rocks, not in terms of their landscape, but for the fact that he could recognize that there was this interesting relationship that he documented, that as you walked through these glens, and the little red dot in the bottom left corner there, near the bottom left corner of this very simplified map, is where I took the photograph that I showed you previously. What Barrow recognized was that as you walk south to north through the Angus Glens, you go through a progressive transition of mineral types from chlorite to biotite, biotite to garnet, garnet to starlite, starlite to kyanite, kyanite to sillimanite. When we're teaching students this in classes, this is recited like a litany to recognize this transition of these minerals, one from the other. Barrow documented this based on just keen, insightful observation. What we now know is that Barrow's observations in the Angus Glens can be related to our recognition and understanding of how these minerals form beneath mountain belts. Here's you standing next to your famous, your favorite Monroe or favorite mountain belt. And if you could go below your feet to depths, what you would see would be this transition that Barrow documented in the Angus Glens, and that people have begun to study, in which they can relate these minerals to pressure temperature conditions. In this rather complicated diagram that I've shown you on the right is showing you pressure as you go on the y-axis, with pressure increasing upward, and temperature increasing from left to right on the x-axis. And this rather complicated array of mineral relationships based on experimental work, theoretical work, thermodynamical constraints can be highly simplified into a diagram that's a bit more cartoonish, but gives us exactly the same information. In this case, what we're seeing is as you come down the y-axis from the top, you're going to increasing pressure, and that pressure is translated over on the right in the y-axis to depth, that is depth below your feet. And along the top on the x-axis is temperature increasing from left to right. So if we now take a look at the position of where these minerals occur beneath our feet, you know as you go down at depth, you increase pressure, and as you increase pressure, you increase temperature. And therefore, this relationship between these minerals and pressure and temperatures allow us to map onto a PT, that pressure temperature diagram, where they would occur. So minerals like chlorite and biotite occur down at 2, 3, 4 kilobars of pressure, that is 5, 10 kilometers of depth. It turns it to 300, 350 degrees C. You can go down to garnets, and you can see that they are increasing in pressure and temperature, somewhat higher temperatures, higher pressures. Go into sillimanites, migmatites, and these types of sillimanite, these types of minerals and rocks, you're down to even greater pressures, down to where rocks begin to melt at pressures and temperatures that are now very similar to what we see in the northern, or in the highlands, in that road cut, these Lewisian gneiss rocks, in which the mineralogical assemblages and their textures allow us to be able to infer, based on these types of pressure temperature diagrams, that those rocks had to form at about 30 kilometers depth and around 700 degrees Celsius. This is all based on Barrow's recognition that there was this systematic change in mineral composition as you go north to south in the Grampians. If we then marry that to our understanding of how these minerals form in terms of continental crust and beneath mountain belts, basically what the Grampian Highlands represent based on Barrow's recognition is a mountain belt that was turned on its side. And therefore, as you drive from, say, Stonehaven to Aberdeen, or from Dundee to Pitlochry, you are essentially going across a piece of continental crust that was an ancient mountain belt that has now been rotated on its side. That's the kind of geological heritage that's preserved here in Scotland, and there are very few places in the world where you can go over such a short distance to see this so readily and so well developed and preserved. Now, if you're going to do that, rotate and twist and deform mountain belts, you have to cause deformation. You have to cause faulting. And this is where we go to our third geological hero, Charles Lapworth. Now, Lapworth is known for studies that he did that related to biostratigraphy, that is using fossils to be able to recognize how rocks are related to one another from place to place, stratigraphy. And he did this working on graptolites in the southern uplands, a marine invertebrate that is very dominant during the Ordovician. But Lapworth's contribution to science went far beyond that, particularly structural geology. All of you have been up to Durness, or many of you have probably been up to Durness. This is right up in the top northern part coastline of Scotland. This is Durness Beach. You could walk along there. And the rocks that you would look at there exposed along the beach have a funny name. They're called oyster shell rocks. They're called oyster shell rocks because, as this pencil is pointing to this feature, that light colored feature, it looks like an oyster shell. It is calcium carbonate, but it's not an oyster shell. What it is an absolutely thinned, pulled apart, smeared out portion of a very thick succession of limestone rocks. Here exposed at Smoog Cave at Durness. And again, if you're there, you would see these oyster shell rocks. You drive 4 or 5 kilometers or 3 kilometers, really a little bit further to the east. What you would see are these thick limestones. And what Lapworth recognized was that this oyster shell rock was formed as a result of faults that ground up, smeared out, stretched out these other rock layers to make them a very thin remnant of their former thick selves. And he could see this even in thin sections. These are thin slices of rocks that you can cut and have light pass through them. And at the bottom, you can see this quartzo-feldspathic. It's a gneiss, and you can see how big the crystals and the grains are. And as you go upward, there is this increasing decrease in the size of the crystals and the grains. And this is what Lapworth recognized as a myelinite. That is a grinding of these rocks into smaller and smaller fragments. And we can see this in many places in Scotland. And this is another very well-known geological outcrop. This is near Kailaskew. It's called the Geological Sandwich, and that name stems from the fact that what you can see are these layered rocks that I've highlighted here in light blue. They are Cambrian-Ordovician in age, about 500 million years old, and they are sitting unconformably on this Archean gneiss, the kind of rocks that I showed you in the road cut image, these Lewisian gneiss rocks that are around 2.5 to 3 billion years old, and they are overlain by a major fault by Archean gneiss. That is, then the Cambrian-Ordovician is sandwiched between these layers of very old rock along a fault in which you can see these comminuted, ground up rocks forming these myelinites. And what Lapworth recognized is that rocks can be pushed over the top of one another. They can be thrust over. They can be moved horizontally. And that is an important insight because most geologists up and through that time, and even to this day, there is argument about how much the force of gravity is required to deform rocks, that is, move them vertically up and down, versus the forces required to push rocks over the top of one another. And Lapworth was fundamental, giving us the observational database that allow us to understand the type of processes that allow rocks to be thrust over or moved horizontally over one another. And the reason that's important is because we show you these types of highly simplified cartoons about what Earth's plate tectonic template looked like in the past. And here, if we would have been able to be in a spaceship and look down on Earth, is what Earth's continental land masses would have looked like 600 million years ago. Circled in blue is where Scotland was located. Circled in red was where England was located. And as we march through time, we can see that the continents are shifting around on Earth's surface horizontally. They're moving horizontally across their surface. They're forming myelinites. They are creating these faults that Lapworth documented. And we can step further through time to see how England and Scotland are approaching one another. And finally, we know as the story goes, then God is telling Scots that I'm going to create this beautiful land for you, for beautiful glens with Ushkaba, this beautiful elixir of life, water of life, whiskey, And you're going to think that you've landed in paradise, but wait till you see who I give you for neighbors. Well, this is when the neighborliness occurred in the sense of a major orogenic episode when Europe and North America collided to form the Caledonian orogeny. And we know when we form orogenies, that is when continents collide with one another, you form mountain belts. And so 400 million years ago, when England was joined to Scotland, we created an ancient mountain belt. And it would have looked something like this. This is the Southern Alps in New Zealand, but nevertheless, it would have been this majestic mountain range. And what I want to highlight here is Hutton's concept of the cycle of rejuvenation and decay. Here you have created a mountain range, and there we can see in the foreground this beautiful braided river system causing erosion and the cycle of decay in which these large boulders and clasts of these roundels cobbles being derived from the erosion of the mountain are being transported by this river. And we can see this preserved in the rock record here in Scotland. Dunnottar Castle along the east coast of Scotland, just south of Aberdeen at Stonehaven. In this little box that I've highlighted. And there we see boulders that are the size of your head, representing an ancient stream, just like what we saw in the previous photo of the erosion of the New Zealand Alps. This is the evidence for the erosion of the Caledonian Mountains. Therefore, in Scotland here, 380 million years ago, we can see the development of ancient streams, eroding ancient mountain belts, formed the continental crust that if we drive a little bit further north in Scotland, we see 3 billion years ago, 2.5 billion years ago, the rocks that form some of the oldest continental crust. We can see granites that are on the order of 400 million years or so in age, 450 million years or so in age, that helped to form this continental crust through time, all represented by Hutton's concept of the cycle of erosion and decay, here 380 million years ago. For Hutton at Siccar Point, the same type of relationships. We can see Lapworth's contributions telling us that we can have rocks moving sideways, horizontally over one another, just like plate tectonics requires them to do. So there's this enormous amount of insight that comes out of our recognition of the rocks in Scotland and our understanding of those rocks in Scotland. And now I want to talk about, lastly, we know that we're no longer part of North America in terms of this Caledonian orogeny, that we are part of Europe, although soon not to be, given our Brexiteers. And this is the idea that we can see evidence for how ocean basins form. Here's the North Atlantic, and through the middle of the North Atlantic is a mid-oceanic ridge. It's known as the Mid-Atlantic Ridge. And what we want to do is go to Iceland, because here you can see physically that ridge exposed subaerially, in which new oceanic crust is being created. Again, Hutton's cycle of erosion and decay. And when you go there, there it is writ large for you to be able to see the idea that we have this mid-oceanic ridge fault separating these continental, these oceanic plates and continental plates, the splitting apart of Europe from North America, and its erosion forming these beaches being transported by the sediment in the river system, just at the right-hand side of that photo. And then on the right-hand image, the creation of new oceanic crust by lava coming up from magmas at depth. And some of those magmas might well be forming rocks that will fractionally crystallize to form granites. All right. This is what it looks like in the modern. Here's lava flows, there's volcanoes. We come to Scotland, the west coast, we can see lava flows and we can see the remnants of volcanoes, but these are 50 million years old. So we see them forming today in Iceland, but we saw them forming, but we have the evidence of them forming 50 million years ago here in Scotland. How can we relate the two? Well, if we look at the age of oceanic crust, and this is a map which is showing us age of oceanic crust. As you move away from oceanic spreading centers, the crust gets older. Here's a diagram that simplifies this up in the North Atlantic. There's the ages highlighted by these different color bands of oceanic crust progressing outward 50 million, 150 million years old. But what's interesting is if you go to the top of the map, you can see the southern part of Greenland in the center of that image. You can see Iceland off to the top right. If you look at the middle left, you can see Eastern Canada, the maritime provinces. And then down in the bottom right is the west coast of Africa. So as you go north through the North Atlantic, oceanic crust gets younger and younger. And if you get up to the position of where Scotland would be, and it's not on this map, but you can just see in Ireland poking out at about the 2/3 of the way up on the right, there is no oceanic crust that's 150 million years old. It's only around 50 million years old. And if we focus in a little bit more, what we see is that that 50 million year old crust is what was generated by those volcanoes that we have preserved here on the west coast of Scotland, identical to what we see in the present day Icelandic mid-Atlantic ridge exposure. In the bottom right of that right-hand image, you'll see this funny Y-shaped feature, and that I want to highlight because that is the Jurassic basins of the North Sea. The North Atlantic tried to open up where the North Sea is, but it failed. And it failed, and the opening then jumped to the Icelandic hotspot where it was successful to form the North Atlantic. But what I want to point out is that the economy of Britain for the last half a century, British wealth, is based on the fact that an ocean basin failed to open in the North Sea because we have the entire North Sea oil resource that fueled this economy for tens of years. Okay. There's our 3 billion year road trip. We've kind of gone counterclockwise around Scotland in terms of looking at these various areas that the Scottish Geological Trust is trying to highlight in terms of the richness of the ideas, the richness and beauty of the rocks that they preserve for people to come to see at any time for free for the most part. What I'd like to do now is take you then on a short journey of talking about 3 other aspects of Scottish geological heritage, which gave us great insights into aspects that are still being studied today in terms of our thinking of, in this case, biospheric evolution. Charles Darwin's statement in terms of the origin of the species from a simple beginning in this form's most beautiful and wonderful have been and are being evolved. And that's a beautiful evocative statement in which we recognize that evolution, biospheric evolution, goes from these simple forms to these myriad of forms, this idea of this constant evolution to more and more complex life forms up into us. And if we think about this in terms of Hutton's idea of deep time, we always like to represent geological time as a clock. And if we did that in this instance and start the clock at midnight last night when you were asleep, and if we go to, say, 3 o'clock in the morning when you were having your dreams, life on Earth would have looked like this, these simple bacteria. 6 o'clock in the morning when you were beginning to think of waking up, maybe taking the dog for the walk, feeding the cat, you'd still only have these simple bacterial life forms. 9 o'clock in the morning when perhaps you were eating your breakfast, the same simple life forms. 12 o'clock noon, considering thinking eating your lunch, simple bacterial life forms. 3 o'clock in the afternoon, perhaps having your cup of tea, thinking about getting ready for this talk. And now listening to me at 6 o'clock in the evening, from midnight, Earth's biosphere would have looked more or less the same, these simple bacteria. It wouldn't be till 9 o'clock this evening when all of you will be sitting down listening to Michaela Strachan talk about Autumn Watch coming out of Tensmere Forest, when we would reach a time when those life forms that I showed you in terms of what Darwin was talking about first appeared. Now, as beautiful and as wonderful and as evocative as that concept is of life evolving, what is perhaps, at least to my mind, one of the most significant biospheric evolutionary steps is the simple fact that for the vast majority of Earth's lifetime, 3 billion years or more, 3.5 billion years, life existed in the ocean. And it is this step out of the oceanic womb onto continental landmasses, formed from granites in large part, that is key to our recognizing how Earth and how life has evolved on Earth in terms of coming out of the ocean, the marine realm, into the non-marine and subaerial realm. And if you think about it, living on land is a pretty miserable existence. When you're in the ocean, you have a constant food supply, pretty much a constant temperature. On land, organisms are exposed to heating, drying, freezing, thawing, all sorts of temperature extremes, different amounts of nutrients, wind, etc. So it's not easy living on land. And the evolutionary step by which that occurred is something that people are really studying and trying to recognize how it happened. And again, we can come now to Scotland and our geological heritage to begin to understand when that occurred and how it occurred. And our last geological hero, our fourth geological hero, sorry, I want to talk about is Jethro Tull, not Jethro Tull. This is Jethro Tull. He was one of the original geologists working up in the Highlands in the mid-late 1800s. And what he recognized by looking at the Torridonian rocks, which are about 1 billion years old, and these rocks form some of the most aesthetic landscapes and evocative landscapes that I know of anywhere on Earth, these Torridonian mountains. He looked through his microscope and he saw features that look like this. Now, these aren't the ones that he saw. They're very similar to that. This is a study that was done about 40 years ago now. But these are fossil spores. These are microorganisms. They're about the size of your hair. If the diameter of your hair, these more circular looking ones, the long one is about what the thickness of your hair would be. This is a study that was just done a few years ago in which those images have now been enhanced, and you can see these are beautiful images or beautiful photos of the type of organisms. These are simple eukaryotic organisms preserved in the Torridonian rocks, which are non-marine rocks. These are potentially some of the earliest life forms on land, preserved here in Scotland. When you see these in the rocks, they don't look like that. You need a microscope to see what you see on the left. They look more like this. They just look like these wrinkle marks. And as a matter of fact, that's what they are called. These microbially induced sedimentary structures are known as wrinkle marks. Okay, so we can look at the rocks. We can understand aspects, continental formation. We can understand aspects about faulting. We can understand aspects about how we begin to understand orogenies and mountain belts and the erosion of mountain belts. We can also begin to look at these rocks to give us deeper insights and understanding to biospheric evolution. Climate change is on everybody's mind. The Pleistocene glaciation started around 1 million years or 2 million years or so ago, and we're now accelerating the melt back of these glaciers through global warming at a rate that's been unprecedented for the most part. But we know Earth has gone through dramatic climatic changes in the past, and trying to recognize the natural mechanisms that generate climate change from those that are produced by us, by mankind, humankind, anthropogenic forcing, is taking up an enormous amount of intellectual capital, as well as a lot of financial capital in terms of funding research. But we can look at glaciations that were far more extreme, climate changes that were far more extreme. This is known as Snowball Earth. This was a time when Earth's entire surface, or almost the entire surface, was covered with ice. This is 600, 700 million years ago. And to begin to understand how these types of climatic catastrophes occurred and how they ended, how they were ameliorated is something that can be understood from here in Scotland. And we can go to the west coast of Scotland, this beautiful set of small islands, the Garvellic Islands. This is a short boat trip from Oban. And what you see there in the Garvellic Islands are features in the rocks that look like this. The top image is a boulder, and what I've highlighted with thin yellow lines is the boulder has bulldozed the underlying substrate to form this buckle underneath it when the substrate was mud. The middle photograph shows a series of boulders aligned one behind the other like a train, and the bottom image shows a clast that looks like it's been shattered, like it's been hit with a hammer. On the right here are images based on modern day processes where we can see how these features formed. These were generated by glaciers moving over Earth's surface and then melting back. The top image shows what's called an ice push structure, where a boulder has bulldozed or plowed the underlying substrate, just like the image in A on the left. There's the boulder train that formed when the glaciers melted and the rocks settled down through the ice. And at the bottom, you see a frost-shattered clast due to freeze-thaw conditions, just like the one on the left, but those images on the left are, 700 million years old. We can see larger features. This is along the southwest coast of the Garvellics. That's a cliff face that's about 30 meters high. The locals call it the bubble. And what it is you can see these rocks are folded into this big U shape. We can see exactly the same type of features on the coastlines of the North Sea, in terms of where ice was coming out of the North Sea during the last glaciation and the Pleistocene and shoved the underlying chalk and substrate into these broad folds like you see on the right. So we can understand ancient processes by recognizing these features in the modern, and then begin to think about, if we had climate change in the past, what were the mechanisms by which that occurred relative to what we think is happening today. And yes, for our last stop, we're going to go to the moon. I've circled where the Apollo 12 landing site is on the moon. And on the right is a rock that was collected there, sample 12009. At the bottom image, that's Ellen Bean. He's coring. This is not him collecting that rock, although I think he did collect it. And that rock was brought back to Earth like many of the Apollo rocks were. And to understand that rock, we actually have to go to Rum, the Isle of Rum, off the west coast of Scotland. Rum was an ancient volcano. The geological map on the bottom right shows you the distribution of the different rocks associated with that volcano. But on the west coast is Harris Bay, and that's known for a particular form of the mineral olivine, which occurs in these very needle-like acicular crystals. And you can see these three images there which show this mineral. It's called harrisite. And the experts at the time on harrisite, Harold Drever, who was a professor at St Andrews, and his student, Colin Donaldson, who was my colleague for 15 years, and 20 years, Colin just retired 4 or 5 years ago. It was Colin who, as an undergraduate, was called to NASA headquarters in Houston, Texas, to examine the moon rocks, and particularly 12009, because when they cut open that rock, the scientists at NASA saw these thin acicular crystals, and they had no idea how they formed. They knew that Harold Drever and Colin Donaldson had been working on these, and therefore our understanding of how harrisite forms based on the volcanic rocks of Rum has given us and has shed insight into how processes operated on the moon. So we have today's Earth system, which is the end product, at least to this point in time, of about 4.5 billion years of geological processes. And over that time span, we can come to Scotland to find evidence about key pivotal periods in the transformation of our planet from how it formed 4.5 billion years ago to its present system. We can go back 3 billion years ago in this image when Earth's atmosphere was probably much more methane rich, hence the orange color, and think about how the earliest continental crust formed by studying Scottish rocks. We can move forward in time to here 1 billion years ago, and in this instance, the Earth is green because photosynthetic process, the oxygenic photosynthesis have been taking place, making the atmosphere oxygen rich. And we can think about aspects of biospheric evolution, such as this major evolutionary leap when the biosphere developed the means by which you could leave the oceanic womb and migrate onto land. We can look at rocks that allow us to understand some of the most dramatic extreme climatic changes this planet has ever undergone in terms of the Snowball Earth. And we can take all that understanding and begin to think about how we can relate the geological processes of the past to what we can recognize today in terms of the planet we live on now. And we can even use Scottish rocks to tell us about how our sister planet, the moon, formed. All of that is at the heart and soul of what Geobus and the Scottish Geology Trust do. And if I could stand in front of you and look you in the eye, I would ask you all to stand up and give a standing ovation to these two organizations who are bringing this richness in geological heritage, geological ideas, and the kind of research that's going on even today to the general public. So we have to thank them, and I have to thank you for listening to me this evening. Thank you.